You know when you see a high-performance engine part, or a sleek jet wing, or maybe even a life-saving medical implant? What do you see? You see perfection, right? A flawless, polished surface that just screams quality and precision. But that perfection, well, it's a carefully won battle against an enemy you can't even see.
No, really, think about it for a second. What is it that makes something look and feel like a premium, totally reliable piece of engineering? Is it just the shiny finish? Or is there something else going on? A hidden world of detail that our eyes just completely miss?
Well, it turns out, beyond that flawless look, there is a microscopic battle being waged. The smoothness we admire is actually the result of controlling a chaotic, rugged world of microscopic mountains and valleys that exist on the surface of pretty much every manufactured object.
That's right. If you could zoom in on what looks like a perfectly flat piece of metal, you wouldn't see a straight line at all. You'd see a mountain range, a jagged, rugged landscape of tiny little peaks and valleys, where the distance from the highest peak to the lowest valley might be just a few millionths of an inch. It's wild.
Okay, so let's get into what this enemy actually is. Let's define it. We're talking about surface roughness. What exactly does that mean?
At its core, surface roughness is just the measure of all those tiny peaks and valleys. It's not some natural feature of the material itself. Nope, it's a texture that gets left behind by the very processes we use to shape it, like machining, the process of cutting, grinding, and shaping raw material into a final part.
And this contrast just perfectly illustrates the huge disconnect between what our senses tell us and what's actually there. Our eyes and hands, they perceive a smooth, continuous line. But physics reveals this dramatic, jagged reality underneath. We're really only sensing an average, completely missing all the microscopic drama. But here's the thing, this rugged landscape isn't random. It's a direct consequence of decisions that are made during manufacturing. And if it's caused by a process, that means it can be controlled by that process. Engineers have a set of levers they can pull to control the final outcome.
And these are the main levers right here. Think of a machinist like a chef, okay? Cutting speed, that's how fast the cutting tool is spinning or moving across the metal. That's like how hot the stove is. The feed rate, how quickly the tool advances into the material, is how fast you're stirring. The depth of cut, how much material you remove in one pass, is how much you're trying to cook at once. And the tool type, well, that's your choice of pan. Every single one dramatically affects the final surface.
So the crucial point is that getting this recipe wrong is what creates our microscopic enemy. Go too fast, too slow, too deep, or use the wrong tool, and you end up with a surface that's way rougher than you want it to be.
Okay, so a rough surface is a manufacturing flaw. Got it. But why does it matter so much? I mean, the consequences go way beyond just how it looks. Those microscopic peaks and valleys have some serious real-world consequences. Of course, it diminishes the look and feel, but more importantly, those rough surfaces create more friction, which causes parts to wear out faster. They dramatically shorten the fatigue life of a component, and they give rust and corrosion these perfect little hiding spots to start growing. And all of this can ultimately lead to one thing: catastrophic component failure. And this quote, wow, it just nails the danger perfectly. Each one of those microscopic valleys is a stress concentration site. So imagine a piece of paper with a tiny little tear in it. It's incredibly easy to rip it further from that one spot, right? Well, a microscopic valley on a metal surface works the exact same way. It focuses all the stress on that one tiny point, making it the perfect place for a crack to start. And this isn't just theory. Look at these examples. For high-strength steel, the kind used in landing gear and crankshafts, it means a shorter life. For Inconel, a superalloy used in the hottest parts of jet engines, it can mean voids and cracks forming right there on the surface. For composites and aircraft wings, the actual layers can start to peel apart. It really doesn't matter what the material is. The danger is universal. So, knowing the stakes, how do we fight back? How do engineers and scientists team this microscopic landscape and build the path to a truly perfect surface? Well, for a long time, the approach was basically trial and error. An experienced machinist just developed a feel for the right settings, often through years of experience in countless ruined parts. But today, we're moving from an art to a science, using predictive intelligence and brand new processes to get it right the first time, every single time. And the tools we have now are just incredible. We're using hybrid AI and genetic algorithms, which is a type of AI that basically mimics natural selection to find the best possible solution to predict what the surface roughness will be before a single cut is even made. We're using these models to optimize those machining parameters we talked about earlier. We're developing advanced techniques like laser polishing, which literally melts the microscopic mountain peaks down into the valleys. And we're applying these same principles to 3D printing to create smoother parts right from the start.
And that is the ultimate takeaway here. This entire battle against the unseen enemy isn't just about making things look good. It's about engineering products that are fundamentally better, more durable, safer, and higher performing. That smooth surface is really just a sign of all that hidden quality. So, the next time you pick up your smartphone, or admire a performance car, or even just use a high-end kitchen knife, take a closer look. Now that you know what's going on, what perfect products in your life depend on winning this invisible, microscopic war?